for example, our mu hat or pi hat, these are values. Okay, so this is a number. This is the number that we compute from the data. If, for example, our mu hat, sum over I of 1 over n, sum over I of xi. Okay. We can define something else called an estimator. Is a random variable over many possible data sets. Okay. And the estimator is 1 over n, sum from I equals 1 to n. But now instead of taking the samples, I assume that I have random variables. Okay, and this xi is a random variable for each sample. And we assume it's from the true distribution. So xi is distributed according to p of xi, the true distribution. Okay, so what we have is, we assume each sample is actually a random variable. And we can think about the idea of, I collect one data set, I get a set of samples, I can compute my estimate of the mean. And the next day I can collect another data set, and I compute an estimate of the mean. So actually there's many possible means that I can compute based on the particular set of samples that I happen to get. Okay, and then the question is, how good is that estimate over the long run, over many days? Okay, so the way we quantify that is, because they're random variables, we can do things like compute the expectation of the estimator. And if the expectation of the estimator is close to the true parameter, and that means on average we can get the right answer. So since the estimator is a random variable, we can calculate the mean and variance. Okay, and this mean and variance can tell us and quantify how good is the estimate. Okay, and the way that we do that is we'll look at two quantities of the estimate. One is called the bias, and the other is called the variance. Okay, so how do we measure goodness of an estimator? First one is, will we get the right value? So we're doing parameter estimation. There's a distribution that we assume that's there, and we hope that we can get that real value that we get. Okay, so the question is, will it converge to the true parameter, the true value of the data? The true value is the one from the distribution. Okay, and we can quantify this with the bias. So the bias of our estimator data hat is the expectation over all the samples, x1 to xn, of theta hat minus theta. Okay, so this is the estimator, and this is the true value. Because the true value doesn't depend on the distribution of x, the expectation doesn't operate on it. So we have basically the expectation of theta hat minus theta. The x1 is a random variable corresponding to the first sample that you collected. So when you actually collect a sample, then you are drawing from that distribution. And every time you collect a set of samples, this is the first sample that you use. And we assume that all the samples are distributed according to the true distribution. Okay. So remember, this x1 is defined here. Okay. So we hope that the bias should be 0. That means that on average we can get the correct answer. If the bias is non-zero, that means that no matter how much data I give you, you will never get the right answer. You'll always be a little bit off, or a lot off. So if the bias is non-zero, we can never get the true value of the data, even with infinite samples. Okay, so this bias is measuring the expressiveness of the estimate. Okay, so that's whether you can get the correct answer or not. Okay, the second question is, how long do I have to wait before I can get the correct answer? Or in other words, how long will it take to convert? Or how many samples do I need? Okay, and to measure this, we'll use the variance of the estimator. Is the expectation over the sample random variables of x1 to xn of the estimator theta hat minus the expectation of theta hat squared. And what this is measuring is uncertainty. Uncertainty or variability of the estimate. Okay, so if I have an estimator that has no bias, by 0, but my variance is very large, then maybe it's not very good. That means that I can get the right answer, but I need a lot of samples. Or on average I get the right answer, But for any particular data set, that would be very far off. So we hope also that the variance is close to 0. Okay, any questions? Okay. So let's try this out for calculation. Let's say you get a sense of this. Okay, so our estimator is mu hat 1 over n, sum from I equals 1 to n of random variable xi. Okay, and then what we want for the bias is the mean of that. From x1 to xn of mu hat. And I can substitute in for my mu hat. It's an expectation of x1 to xn of 1 over n, sum from I equals 1 to n of xi. Okay, so here I have an expectation over multiple random variables, and then I have a sum of those random variables. So actually, the expectation only applies to each of the random variables. Okay, so this is the same as 1 over n, sum from I equals 1 to n of the expectation with respect to xi of xi. What's the expectation of xi? Well, it's the mean, the true mean. This is the mean. Okay, and then I have a 1 over n sum of mu. So that gives me n mu's. N mu divided by n. So the mean of the estimator is mu, the true parameter. Okay, and then because the mean is mu, so that means the bias of mu hat is equal to mu minus mu, which is 0. Okay, so that's good. What about the variance? The variance of mu hat is the expectation from x1 to xn of mu hat is 1 over n, sum over I of xi, minus the mean of the estimator, which we just calculated mu, squared. And you can work it out. It's one of the problems in the problem set. But eventually what you'll get is the variance of mu hat is 1 over n times the squared. Okay, so what does that mean? So n is the number of samples. So as I increase the number of samples, my variance, which is good, that means that I get closer and closer to the true height. The variance converges to 0 as n goes to infinity. draw a graph. So suppose the x-axis is the number of samples, okay, and then we have a true mean, which is here. This is mu. Okay. And what it's saying is, I basically have a 1 over n relationship. Variance. So it gets something like this. These are like the standard deviation bars of the distribution. So I have, as I have more and more samples, my standard deviation gets smaller, and eventually my distribution of the estimator is converging to the true value. It means that I'm more likely to get the correct value, something close to the correct value. So here you can see distribution. So the G of mu hat converges around mu and n increases. So this looks good, right? With the estimator of the mean, the Gaussian, the bias is 0, and the variance is 0. Great. Okay, so let's see with the variance. So another example is the Gaussian variance. So if I look at the expectation of sigma hat squared, okay, it won't do them. Eventually, if you work it out, it's if you're interested, this is problem 2.12 in the problem set. So it'll help you to go through that once you do it. Okay, but eventually, what you get is the mean of the estimators n minus 1 over n times the true value sigma squared. It's the same as 1 minus 1 over n of sigma squared. Okay, so what does that mean? That means the bias of sigma hat squared is minus 1 over n. So, for large values of n, my bias is 0. But unfortunately, for small values of n, my bias is 1. Okay, so sometimes you'll see, if I want to make it unbiased, then what we can do is just multiply our estimate using n over n minus 1. Okay, so we can make it unbiased by multiplying by n over n minus 1. Okay, so we have sigma hat squared is n over n minus 1 sigma hat squared. Okay, so here you can see if I take the expectation of sigma hat, I'll have n over n minus 1 times this. N minus 1 over n cancel, and I'll just get back to sigma squared. Okay. If I do that, then I'll get n over n minus 1 times 1 over n, sum over I of xi minus h squared. Okay, and then these n's cancel. And you get 1 over n minus 1, sum over I of xi minus h. Okay, so sometimes you will see this formula for the variance. It's the unbiased estimate. Okay, any questions? Okay, so in general, you can do this for any estimator that you want. Not just maximum likelihood estimate, you can any way to take the values, or to derive the values from the estimate. And the question is why we usually use maximum likelihood estimate. Okay. And in general, there will be a trade-off between the bias and variance of the estimator. And the important thing about the maximum likelihood estimate is that it's the best estimator that you can get. And people have actually proven this mathematically. Okay, and that by itself is a whole course on parameter estimation. But I'll just tell you the result now. So this is important asymptotic properties of maximum likelihood estimate. Okay, the first one is you saw it already. Okay, so as you increase the number of samples, you get an unbiased estimate. Okay, so that's true for the estimator of the mean, but it's also true for the estimator of the variance. As I increase the number of samples, here my denominator gets really big and my bias goes to 0. Okay, so the first property is the consistency, or consistent. That means that as n approaches infinity, the estimated value converges in probability to the true value. Okay, or in other words, it's asymptotically unbiased. Okay, so that means that as long as I have enough samples, I will get the true answer. Okay, but that's not all. Okay, so this maximum likelihood estimator is also efficient. What it means is that it has the lowest possible variance of any unbiased estimate, any possible unbiased estimate. Okay, so this estimator achieves something called a Cramer-Rao lower bound, CRLP, as n goes to. Okay, and the Cramer-Rao lower bound is a theoretical bound on variance of the estimator. The CRLP is a theoretical bound on the variance of any unbiased estimate. Any unbiased estimate for a given distribution of x. Okay, so what it means is that this is the lowest possible variance you can have, theoretically. And the Khmer-Rao lower bound, that's the Khmer-Rao lower bound. And the maximum likelihood estimator achieves this lowest variance. So it's the best. You can't argue with that. So in other words, no unbiased estimator can get lower variance. Okay, the key here is unbiased. So maximum likelihood estimator is consistent, so it's unbiased, given enough data, but it's also efficient, means it's lowest variance of the estimator possible. Of course, I can have estimators that have zero variance. Right? If my estimator of the mean is 5, the variance is 0. Right? Because I always predict 5, no matter how many samples I have, therefore the variance is 0. But my bias is not 0. So this is the statement for unbiased. Any questions? Okay, so this is a theoretical reason why people use a maximum likelihood estimate. Okay, so the final part of the lecture is actually to use this maximum likelihood estimator somewhere. So this is for supervised learning. So we use the maximum likelihood estimation for regression. Okay, and the idea is that we have a supervised learning problem. Where we have a data set consisting of x i's and y i's. So we do something like this. This is x, this is y, and then I have some values like this. And my goal is to learn a curve, to regress a curve for these data points. So x is the input, the real number, and y is the output, it's also a real number. Okay, so the simplest thing to do is we can try to fit this curve as a polynomial function. So suppose we look at polynomial functions. Okay, so then I can define f of x with given theta as the sum from equals 0 to k of x to the d times some weight weighted. Okay, so for example, if d is 2, then I have eta 0 plus eta 1 times x plus eta 2 times x squared. So that's a quick but I can be a little bit smarter. Instead of writing it out like this, I can write it in terms of a vector, ix, inner product with a parameter vector theta. Okay. And here the ix is a vector is 1 x squared, so forth, to x to the k. And my parameter vector theta is theta 0, theta 1, theta k. Okay, so you can see if I take the inner product of these two, I get back a polynomial. Okay, so this is the function we want to estimate, but we don't observe the function value. We observe noisy versions of the function value to make it more difficult. So we assume we observe noisy output. Noisy output y given in x. And we're going to say that y is f of x and theta plus epsilon. And the epsilon is the noise, which we'll say is a normal distribution with zero mean and variance sigma squared. So this is the observation noise. Any questions? Okay, so that's the setup. Okay, we have a data set. We want to regress a function to this data set. And for now, we just look at polynomials. Okay, and we can write it in terms of, this is we call a feature vector. Okay, and this is a parameter vector. And this happens to be a linear function of the parameter. Okay, and then we observe a noisy output with Gaussian noise, additive Gaussian noise. Okay. Equivalently, we can say the following. Okay. If you look at this formula, where is the randomness coming from? So if I know x, I know theta, I get a value. Right? That's deterministic. So randomness is coming from x. So I have some noise, and then I'm adding a function value to it. So I can write the distribution of the output given the x and the theta. And this should be a normal distribution because the noise is normal. And I'm just shifting it to wherever the function value is. So the variable is y. The mean is the function value of x given theta. Okay. And the noise, the variance is another way to think about it is epsilon is a random variable. Therefore, y is also a random variable. So I can write down the probability distribution. That makes sense. Okay, now I have a probability distribution. How do I estimate my parameter theta? I just spent 1.5 hours telling you how to do it. Just use maximum likelihood estimate. So, given a data set, we already have a data set. Just say, use maximum likelihood estimation to find data star. So, data star, argmax theta of sum over I equals 1 to n log t of yi given xi theta. Okay, I won't go through the derivation this time. In the tutorial, we'll actually talk about it. But eventually, if I do some derivation, this is the tutorial. What we get is arg min over theta of the sum over I equals 1 to n of yi minus f of xi times theta. Okay, so what is that? Well, I have my observed value, I have my function value. I take a difference, that's like an error, and then I'm squaring the error, and then I'm minimizing this squared error. This is these squares. And this squares estimation. Okay, and then you do a little bit more math. And eventually you get a solution, which is theta star is I transpose inverse I times y. Okay, where the I is a matrix of ix1, ixn, and then the y is a vector of the outputs y1 to yn. Okay, so again, we'll go over this in the tutorial and just give you the sum. Okay, so under this, these assumptions of maximum likelihood estimator, eventually we get that it's these squares summation. And then we get a solution. This is actually the pseudo inverse times whatever. And we'll go through this in the tutorial. The important thing here is what? It seems like, okay, whatever. Right? I have maximum likelihood estimation. I get these squares. So what? What was the point of doing maximum likelihood? Well, the point here is that all of the assumptions of our model are explicit. Okay. With least squares estimation, I just say I'm minimizing the square. I don't know what that means in terms of the model. Okay. So the important thing here is the assumption. So maximum likelihood is more general. And least squares. Okay. And our assumptions that we made are explicit. Okay, what are the assumptions? One assumption is we use Gaussian noise. Okay, another assumption is that we had IID samples. another assumption is that we assume the mean of the noise is 0, and the variance is known. If I don't believe these assumptions, I can change them. If I don't think that the noise is Gaussian, I can change it to some other distribution that I think the noise is. And then my model would be better for my data. That's something you can't do with these scores. So actually this maximum likelihood expression can describe other least squares formulations. So if you want weighted least squares, that means that each sample has its own weight, and you have a particular assumption about the Gaussian noise. So you can look at problem 2.8. If you want regularized least squares, that means that we have some penalty on the parameters, and we'll talk about this in the next lecture. If you want, you can use like a LP norm type least squares. And this is problem 9. So as I change the norm for least squares, the least squares use L2 norm. So you can change it to L1 norm, you can change it to L height norm, L infinity norm. Okay. Those all have interpretations in terms of probability. So the point is that the maximum likelihood is a general, not just applicable to this problem, but actually to many other problems.